I did want to point out one last other resource I can provide you. Some folks have asked me about power in the context of clustered longitudinal designs. Who was I talking to about that? Are those people still here? No? Okay, well, screw you then. You don't get an example. But I do have a SAS program that calculates power for a level 3 predictor in predicting slope differences across time. So it's children, time nested within children within schools. And so I'd be happy to share this resource too if you care about that. So, all right. So what we have left on top then, am I recording? Yes. Is the last little bit here. Lecture 4. And then whatever else you want to talk about that I can talk about. Here we are. Lecture 4 and example 4. There's a story behind this one too. So it's a short little lecture and a short little example. There's a 2007 paper that goes with this. So we're talking about crossed random effects models for not longitudinal repeated measures. So this is for like experimental folks. So you've talked to me about something like this, and someone else did too. I've had a few conversations with folks. So this one's for you. So I've been saying there's nothing wrong with repeated measures ANOVA when it fits, but there's a long history of trying to shove experimental data into an ANOVA when it shouldn't be shoved there. So when does this work? If you think about experimental stimuli as controlled and exchangeable. So if I'm doing like a classic attention task where I'm searching for an X in a field of O's, after I control for how many O's there are and where the X is located, I'm pretty sure those displays are equivalent. People are really good at making equivalent displays. But if I'm looking at something like real-world pictures, or I'm responding to real words, those differ in lots of ways beyond what I may have measured or manipulated. So what do I do when my stimuli within a condition are not 100% the same? Similarly, what do I do when my conditions aren't necessarily discrete? So what if my item predictor, for instance, for my pictures is the level of salience of some target, where that's a continuous variable? I could carve it up into low versus high, but that's introducing measurement error. What if I want a slope? Or what if I'm doing eye tracking and I'm looking at picture viewing over the course of, say, 6 seconds? I don't want to divide those intervals into arbitrary time chunks. I want to look at trajectories of eye movement behavior across continuous time. Repeated measures ANOVA is tough to do that in without cutting things up. And last but not least, complete data. So if you're measuring response time, tradition has it that you only use response time for trials that are accurate. But people are sometimes inaccurate. And if they are inaccurate on the trials that would have been the hardest, that would have taken the longest, the mean response time that you're left with could be biased because it doesn't have the trials for which the response time would have been highest. We call that missing not at random. So ANOVA starts to break down when you have any of these problems. And focusing more on the first one here in the example that I have. So this is a real study using psycholinguistic data. So I was a graduate student at KU in the psych department, and one Friday after work I was out playing pool with some other grad students, and one of them was Larry. Larry was really bummed because he just gotten a paper rejected. Larry was a psycholinguist, and he studied things like the difference between pint and pint, and he would have long discussions with his colleagues about this. And his paper got rejected because his F2 ANOVA wasn't significant. And I'm like, what the hell's an F2 ANOVA? So he told me, well, you are supposed to see if your manipulation for your word effects is significant in a subject's ANOVA and in a separate item's ANOVA, and it has to be significant in both for the editor to believe that you have a real effect. And he didn't have significance one way, and so his paper was bounced. But it turns out that neither one of these models is a great idea. So what happens is that these different models are different ways of operating on aggregated data. So if I have say 100 items within each of 4 conditions. So I have dimension A, dimension B, and 400 total items. An F1 ANOVA collapses the items within a condition. It might take a mean across items or a median, some kind of summary statistic, and it feeds those 4 means into a repeated measures ANOVA. So response time per condition per person would be an intercept, main effects of A and B, their interaction. Here's my random intercept because that's what repeated measures ANOVA does, the univariate version. Another way to think about it, though, is if you're interested in the effects of the words. You aggregate over the people. So I have N people that responded to all of these words. I could create a mean for item 1 across all my people, item 2 across all my people, and I could subject those items to an item level ANOVA. And that would be a between subjects ANOVA because each item is separate. Each person saw each item only once. So F1 ANOVA then is treating subjects as the random effect by getting rid of any within condition item variability. F2 treats items as the random effect by getting rid of any with the item person variability. And as it turns out, 2 wrongs don't make a right. This is not a new problem. There was an article from like 1973 that pointed out this asynchrony and tried to propose a solution to it that makes use of all the original data to look at both subjects and items as random effects. The problem is that it used least squares, and so it required complete data. So because people never had complete data, they came up with alternatives such as this min f prime, which is derived from these F1 and F2 results, or this thing where it has to be significant 2 different ways, which is why Larry was crying in his beer at the bar. Not exactly, but he was bummed. And so at the time, I was thinking, well, I'm doing this multi-level stuff, and it sounds like items are nested in persons, and can multi-level solve this problem and change the world? So I thought, all right, what if we don't aggregate the data? What if we model all the items? So I would have response time for each item for each person. Items would be level 1, persons would be level 2. And then I'd have my intercept here, and here's my random intercept for persons, and here's all my level 1 predictors for the item characteristics. And I thought this was great because I was using all the original data, which means I could have some of the trial responses be missing at random. I could have continuous predictors at level 1 instead of these discrete predictors, and this would be great. The only problem is that this is still wrong. This is the same thing as F1 ANOVA, but only using all the original data. I'm still treating only subjects as my random effect. So here's how we fix it. This is the way that I was thinking about it, as items as level 1 and persons as level 2. But actually, I could have thought about it as items at level 2 and persons at level 1. That would have been equally valid. So what I was thinking of as items actually needs to be split out as a separate random effect. To the extent that these words differ from each other for reasons either manipulated, measured, or unknown, some items are going to be responded to more quickly. That's a random item intercept that is needed. Just as some people respond more quickly on average than other people, that's a random subject intercept. So level 1 is actually trial. It is the unique combination of person and item. Each trial is nested in persons, and each trial is nested in items. So building this model then requires 2 different level 2 units. So here's an empty model that's E only. So all the response time variance in one pile, it assumes all trials are independent. I build up to include a random intercept for subjects, or for persons here, which would allow a correlation of trials from the same person and would allow mean differences between persons and response time. And I add to it another random intercept for items this time. This allows an additional correlation of trials from the same items, and it allows some items to be responded to faster on average. So it is a 2-level model with two different kinds of level 2 units, which are crossed random effects. So putting it all together then properly looks like this. And when we have crossed models, I give up using multi-level model notation and I write it as one equation. So I have a fixed intercept, a fixed effect of an item predictor A, a fixed effect of an item predictor B, their interaction, a random subject intercept, and a random item intercept. So this random item intercept here captures all the within condition variation that I would have thrown away in an F1 ANOVA. If I'm right, if all of the words within the same A-B combination really are the same, then adding this random intercept to the model shouldn't help. But that's an empirical question. Likewise, this random subject intercept captures all of the within item variation that would have been thrown away in an F2 ANOVA. Both of these sources of variation are necessary to be able to test either subject predictors or item predictors accurately. And there's still the residual, which is everything else that's the trial variation that's subject by item. So in here could be things like trial order. If people slow down the longer they do this task because they're getting bored, or if they speed up because they get better at it, that's a trial level, level 1 predictor. It pertains to the unique combination of subject and item so long as items are randomly ordered differently across subjects. So this is a better way of life with a star here, because now there's this whole debate about maximal models. Have you guys read about this stuff? There was a paper where some people said basically whenever you fit these item effects, they have to have random slopes. Not only random main effects, but random interaction terms, or you're wrong. And they had a simulation study that suggested that this was the case, and it sort of took hold. And so now in certain fields, if you don't have what's called a maximal model with all possible random slopes, you're out the door. So this is of interest to me because it flies in the face of traditional logic of model building, where you would do likelihood ratio tests to decide which random effects you need. And so there's an active debate as to whether or not this is reasonable or overkill. And the jury's still out on that. So we took Larry's data from a different study that didn't get published, and we wrote a little tutorial. In 2007 it was published, and it uses data from an experiment with 38 subjects and 39 words. They were actually words or non-words, and it's a lexical decision task. It's response time to decide if it's a word or a non-word. And he had two item predictors, phonological neighborhood, which is like the number of, I don't know, I can't even remember what this stuff means. It's how many words sound like that word. Is that right? Any linguists in the house? Yes? That's right. Woo! I'm a psycholinguistic person today. And semantic neighborhood size, how many words have the same meaning or similar meaning-ish? Well, let's call it A and B. Point is, they're word things. They're word things. And he picked words from a database that were either high or low in these dimensions. Now, they could have been continuous, but he didn't design the study that way. So in looking at an empty means model, and I can show you the output for this, rather than compute an interclass correlation, I think it's more informative in these types of designs to just do a straight proportion of variance. So we start with a model where everything is trial. We added random persons, added random items. And it turned out that person random intercept was 24% of the total, item random intercept was 11% of the total, and trial residual level 1 variation was 65%. So now I point out these two predictors. These were the only things in his data set. So if this is the strongest effect of word whatever in the history of the world, it captures all the variance it possibly could, how much variance in response time is A and B and their interaction going to account for at most? 11. Yeah. These are word things. The only kind of predictor that could explain why some words are faster than others is word things. What kind of predictor would explain why some people are faster than others? Not a trick. People things. Yeah. And trial would be something else that's not people and not item, but some interaction of the two or something specific to the trial, such as the order. So here's the model that we ended up with, and 30% of that 11% was captured by A and B in their interaction, which means a total R-square of about 3%. So in the example, after fitting A, B in their interaction, I did tested random slopes, and those weren't significant, but I also did another model comparison where I took out this random item intercept to see whether the model fit got worse, and it did. So what I was asking is whether or not we got all the item variance such that there was non-significant amount left. So is that 70% that was left significant? It was, which means that all of these items are not exchangeable. After controlling for their neighborhood frequency and neighborhood size, that was only 30% of the reasons they differed from each other. There was still 70% up for grabs. And this is the point where thinking about the modeling differently interfaces with the design, because I remember sharing these results with Larry, and he's like, well, I know, but there's this and this and this and this, and there's all these other things that I've balanced all the words on. I'm like, why the hell aren't they in the model then? Because they would soak up the rest of the variance, that why items are different from each other, and then the item effects he cares about would be stronger. So all of the variables that you are carefully building into your design to make sure that your words are as equivalent as possible in every other dimension, they go in the model. There's a place for them to go because they can soak up the rest of this item variance. So whether or not an F1 ANOVA is acceptable is essentially the same thing as whether or not you have this random item variance left over. Whether or not an F2 ANOVA is acceptable is similar to whether or not you have this random subject variance left over. And actually, we compared our results from this crossed model to an F1 subjects or an F2 words ANOVA or to this Fmin prime, and unsurprisingly, it came out most similar to the F2 ANOVA, because the F2 ANOVA is the only one that treats words as a random factor, as is needed to make sure that the word effects are tested correctly. And Chapter 12 in the book has a simulation that shows what happens. Basically, if you leave out one of the dimensions, predictors that should have captured that item variance are tested inaccurately. So when does this apply to you? Let me give you some examples. So your story earlier, right? You had 4 kinds of trials? Trial types. So 4 observations per person? Or more than 4? 4 observations per person. So she has 4 stimuli. You don't got to worry about any of this, because once you put in the model which is which of the 4, you have explained all the item variance that there is, because there's only 4. But if you had, say, 10 trials of each of the 4, then you would potentially still have variance across those 10 within a condition, and you'd have to worry about having item variance as a cross-random effect to have it be accurate. So the same principles that we talked about in terms of fixed and random readily apply. In this case, you can have a level 2 random effect over the other crossed dimension. So in Larry's story here, for instance, let me go back to this picture. What if some people were, let me see, get the direction right here. What if some people were slowed down more by having a low frequency word than a high frequency word? Is that right? Let me see here. Yeah, low frequency is here, high frequency. So in this case, let's look at the difference between the orange bars. In a high frequency word, right, some people are slowed down more by having a small neighborhood than a large. So this difference between the orange bars, that's on average. What if people were differentially susceptible to this manipulation? That's a random slope. Similarly, this low frequency effect looks like not much of an effect here in the blue. What if people were differentially susceptible to it? What if it was positive in some people and negative in others? That's a random slope. So in your case, you had trials. You told me, I think, about another story where it was same-race couples, interracial couples, or just random pictures. Do you think that there's differences between people and how they respond to interracial couples versus same-race couples? Was that probably like the whole point of the story? Right? That's a random slope. So people things would explain why some people respond more differently to interracial couple pictures than same-race couple pictures. That's a random slope for items over the person dimension. So it's all the same kind of ideas, just within a different context. So these models can be very useful in experimental settings, even when there's no time involved, but you're still talking repeated measures. Sure.
Like in that, I guess Larry's example, like whether the person or whether the participants got the trials correct or not, would that be like another predictor, or?
Well, if they didn't get it correct, their response time was thrown out.
Okay.
But yeah, that's another thing you could do, actually. If you wanted to test whether the response times for inaccurate responses are somehow different, you put in whether it was right or wrong, and then you have a test of that. So, yeah. It's not crossed. Yeah, you put in which is which, and you're done. And you can't have a random slope because you only got 2. It's the same. So it is surprisingly easy to estimate these models in SAS and SPSS. Stata throws up on these crossed models. There were several that I couldn't get to converge at all. I don't know if I was just messing up the syntax or what, but I had a heck of a time getting these to converge. But in example 4, it walks you through the process of building to that final model, starting with E only, adding random subjects in model 2, and then model 3 is our unconditional model before we get predictors. That's on page 3. So the way that it works is 2 randoms. There's random intercept subject equals item, and random intercept subject equals subject. Because they are on separate random lines, there is no covariance between the random effects for an item and a random effect for a subject, as it should be. So it is as if you have 2 different level 2s. And in Stata, it's this weird all R subject thing, and this is why I'm not quite sure I specified it right, but I did get the models without the random slopes to converge in Stata, but it looks like that. And so you end up with 2 different UN11s, one for each dimension. So this is the partition of variance. Because each of these variances has no covariances between them, you can add them up. So the total is just the sum of these 3, given right here. And then I took the straight proportion due to each source. And so that's how I came up with the original proportion of variance, 24% subjects, 11% items. Then added fixed effects of frequency and size. Used the class statement so that I could get least squares means and mean differences. So there's all your classic ANOVA output that you would normally have. It's just that you're getting the right answers. It's always a bonus. Here's me taking out the random item intercept, seeing if the model fit got worse. Yes, indeed. Which means there is significant variation among items of the same type. Then I tried to add random slopes. So random slopes across people in the effective frequency. So the number one way my students screw this up is they put item variables on the item line. It has to be the other one. You can have a random effect of item frequency across subjects. Each person needs their own item effect. You could also have person whatever as a random effect across items, although it's harder to think about that as an example. But if it's an item characteristic, it can vary randomly over subjects only. And likelihood ratio test suggests that I do not have a significant random slope variance, so I kicked it out. But that's what the model would look like. And here's some words. On the last page here, I have two different versions of these words. After explaining just the basic variance partitioning and interpreting each of the random intercepts, I have an ANOVA version of these results using Fs and the language that people would like, and then I have a regression version. So pick the one that your readers are going to be happier with. And then there's the random slopes report of the variant. So this is the same idea, by the way, as how you would handle groups that change over time. So if you say measure kids each semester and they're in a different class each semester, group is time varying. That's not a 3-level model, it's 2-level crossed. So occasion is nested within child, occasion is nested within group, and child and group are crossed because they switch classes over time. So I have an example for that in 945 as well, and it makes use of multiple random statements, one for each occasion basically, to identify the effective group at that occasion. And instead of putting in intercept, I put in a custom 0 or 1 contrast that shuts the intercept on or off depending on whether or not they're actually in that group at that time. So I can show you that example if that's something you need to worry about. But it's the same idea. It's a crossed level 2 random effects model to deal with that, or what's known as cross-classified in the educational literature. So, any questions on that example or on this type of model? So when you need to worry about this is when you have item variance left over after you've put in the predictors that distinguish which kinds of items is which. That's when. Nothing. Next. No, seriously. G-theory models is about variance partitioning, right? That's what this is. It's all crossed random effects. Yep. It's the same. It's the same. Other questions?
So with Larry, sorry.
Yeah, this is Larry. No, Larry Locker. That's him.
So what happened with the item, I guess, differences that he didn't want? Like that 70% that wasn't expected, sort of? Like, what did you do? Like, did you report it, I guess? Or?
You would report it. The question is whether or not your effects are significant when you are correctly predicting what kind of variance they would account for. So only item differences would be relevant in testing whether or not these effects of item things matter. What reviewers were saying is that, well, because of all this other stuff, maybe his controls weren't good enough. And so his F2 wasn't significant. It wasn't this particular study. It was a different study. It was a study in which he had like 150 undergrads but only 20 words. So if you stack the deck with subjects, guess what kind of power you have for subject variables? Yeah. If you only have 10 or 20 words, guess what kind of power you have for word things? Bad. So that was the problem. He didn't have enough power on the item side, but that was all of his predictors were item things. But if you think of it in a repeated measures ANOVA context, you think you need more people, but you don't. So One time I was teaching this, and there was this girl sitting in front of me in my class who was getting madder and madder as every word came out of my mouth. And so I asked what was up, and it turned out that she was in this like never-ending master's thesis data collection where she wasn't getting these item effects that everyone else had gotten, and her advisor kept telling her to get more and more people, but she only had 4 items, and that was the problem. And so she was never, ever going to find it, and she realized this, and she's just like, I've just wasted a year of data collection. Like, yeah, if you care about item things, you need items. People are incidental. No, it's true, right? Like, if you think about the logic here, Larry had no person predictors. He grabbed the nearest undergraduates from the intro psych pool. He measured nothing about them because he does not care about the people. It was all about the words. But people, as it turns out, were 24% of the story. So, yeah. No? No comment? Okay. Other questions? Other questions at all? Not on this, but just in general. Anything in the world of MLM. It's hard to get to everything in 2 days, so I apologize if I'm leaving you hanging on anything. But
that's right. I'm actually, my brain is undergoing a very severe information overload.
Yeah.
But so this is pretty new to me. But is it like conceptually something related to or similar to a level 2 interaction?
Not really. So what I would call a level 2 interaction would be between 2 time invariant predictors, like belonging to the same level 2 unit. If it was a person variable times an item variable, those are both level 2, but they're different level 2s, and so I'd still kind of call that cross-level. But that might be a semantic distinction. In this case, if you had a person variable times an item variable, that would actually predict residual unless you had a random slope for that item variable across persons, in which case it would capture the random slope instead. So it behaves like a cross-level interaction in that case. And yes, as I said at the beginning of the workshop, information overload, yes. You know enough to be dangerous if you have never done anything but this workshop. But my hope is that once you go home, enjoy the rest of your weekends, you can read things more easily because you've had a framework in place and the vocabulary in place to hopefully pick up on what people are saying. So I'm hopeful that this is a good introduction so that you can go and learn more, not only from my book, but from other people's, because people explain things differently, and to hear it different ways and have it make sense different ways is a really good way to get a deeper understanding. And teach it, too. That's the other thing I can tell you. Sign up to teach it, because it will force you to learn it at a level you would never have imagined. I'm still learning. I'm still trying to figure things out, and I've been doing this forever, or what feels like forever, at least, by 4 o'clock on a Saturday. So, anything else I can help you with before we adjourn? All right. Well, thank you for hanging out this entire time. I appreciate your interest